So this first one is an application of machine learning to the estimation of intact rock strength from core logging data. This was a case study that we did at the Newcrest Cadia East mine a few years ago. And this both involved ITASCA, Pierce Engineering, and Newcrest, which was the main client. Brief outline, I'll go through some background on the mine, talk through some project motivation, why did we choose machine learning to solve this problem, talk through some of the data and pre-processing that was done, some details of the machine learning model. I'll be talking through the details of the random forest model in this, talk through some analysis, and then some conclusions we reached. So starting out with some background on the mine. So the Cadia East mine is located near Orange in New South Wales, Australia, and this is operated by Newcrest Mining. So this is an underground mine. So Cadia East is part of a series of kind of gold and copper mines located throughout the Cadia Valley. And it's home to Australia's largest underground gold mine and one of the largest gold and copper deposits in the world. And so a feasibility study began in 2020, which is kind of when we first got involved. We were involved a little bit prior for the pre-feasibility study to expand panel caving operations at the mine, essentially transform this from a fully underground mine to kind of partially having an open pit and then expanding the underground portion. And so some project motivation for this. So a large amount of strength information is required to complete a feasibility study at the mine, right? You want to ensure that, there's enough strength information that, the model is not going to collapse and hurt people. It can be done in a safe way and also be done economically and successfully. And so there was a large amount of data that was logged from 1,300 drill holes. This was close to 600,000 meters of logged data. And this included information on the core logs for mineralogy, alteration, lithology, geotech, various structures, etc. We had a lot of information available to us. Determining point load strength was the primary kind of strength metric they used. Determining this at every meter along each core was desired to be used for the construction of a robust geospatial rock strength model after the fact, of rock mass strength in the mine. And so, right, in an ideal world, we would have a point load test done at every meter, 600,000 point load tests done. But of course, it's very impractical to conduct, this number of tests in a few months. So although, point load testing is simple and relatively cheap, you can't do that many tests in a few months. So our solution was to conduct point load testing on a smaller amount of core and use machine learning to predict the remaining point load strength in the mine and use that to then figure out the rock mass strength and create a block model. So for data and pre-processing, so many core logs recorded irregular segments along the drill hole, right? Some of these you have for mineralogy, alteration, lithology, geotech. These have, tons of pieces of information recorded, but along irregular intervals. So the first step in this process is homogenizing all of this data such that each sample represents a 1 meter section of core. So from all these, irregular intervals, we can map all of this information on these separate spreadsheets to a single spreadsheet where for each meter, we know what all of those pieces of information are, related to the mineralogy, alteration, lithology, and geotech. And so these were all of the features we had in our data set. So some of the raw features, the piece of information they already had on the core logging sheets were things like RQD, fracture frequency, mineralized veins per meter, the rock density, the ISRM rock strength, which is that R hardness test you do with a hammer, the rock color, what the lower contact was, the texture of the rock type or lithology, selvage mineralization, what minerals were present in the core, the rock structure, rock fabric, and then also what point load test machine was used to do the test. Some of them, didn't perform in the exact same way or might have had a more blunt tip giving a slightly different point load test result. And then we also came up with 8 engineered features. So these were features that, didn't already exist in the core logging sheets that we introduced to the model to hopefully be good predictors of strength. And so this was the fracture spacing, which was simply the inverse of fracture frequency. We also scaled it a bit. Mineralization percent sum. This was looking at all of the minerals that were present and adding up mineralization count. Mineralization strength index was relating the Mohs hardness of these minerals and kind of, numerically quantifying what minerals were present in the core and creating a linear index for that. Alteration strength index was similar, but using the alteration minerals and intensity that was recorded. The number of joint sets that were present, we added to the sheet. A fracture feature index, this was simply combining the RQD and fracture spacing together, and we scaled them, and it turned out to be a pretty important feature in the model. Discontinuity frequency index was a frequency of the discontinuities recorded along the core. We also had a weighted DFI that was a separate discontinuity frequency index feature. And so for the model to predict point load strengths, of course, some training data is necessary. Systematic point load testing was performed at every meter along 19 drill holes. So this resulted in 7,700 training samples about. So this was 7,700 point load tests that were conducted. And initially, we tried creating or training a regression model from this. Naturally, you would train the model on these core logging inputs, and you would have it spit out an actual decimal value for the IS50. But we found that, the model yielded very poor results because of noise in the data set. And, I think this is pretty natural, right? Point load testing alone is already pretty noisy. You can perform this test on different points in the same piece of core and get slightly different results. And there's also noise kind of attributed to the core logs, where different people might have written down this information and recorded it in a slightly different way. Because of that, regression just kind of didn't work out, that we weren't able to predict, an exact value very well. Instead, what we did is we tried grouping these values into various classes that we have called IS50 classes in the table here. And so using the Jenks natural breaks algorithm, which essentially finds the best way to split your data set into various classes by looking at the values, we were able to create, different class bounds and group these in classes. So instead of predicting an IS50 value directly, we're instead predicting an IS50 class. And then what we've done is we've converted these then class values to the mean of that class in MPA. And the training counts are shown here as well. We had a lot more weak data to train the model on than strong data. So now we can talk a bit about what model we used. So before jumping into the random forest model, it's important to first talk about the decision tree model. And so this is a kind of a simple flowchart-like model. I'm sure you've seen something like this before, where splits are just binary splits. They're either yes or no questions that are asked. Remember, this model does not exist before we start the training. So these binary decision trees are actually created from your training data. And so using what's called a purity metric, it chooses features from your overall feature set that can best split your classes up, optimally splitting your classes. And so in this case, it was 5 different IS50 classes. And so splits are going to be made from your training data to try to optimally split out all of those classes, asking various questions about your features. And terminal nodes at the bottom of the tree then contain samples belonging to the same class. So you try to split up all of these classes so that they're all pure in the end. And so this can be best explained by kind of showing a simple example of actually building this tree. And so this is kind of an example of, let's say we're trying to predict certain animals in Africa. What animal do we have given various features? And so in the beginning, you start with your training site at the top and the tree doesn't exist. And so using this impurity metric, you try to pick features that best split these classes up. So we can ask a question of, is the animal yellow, right? Yes or no. And so that splits up these classes such that we've moved, the orange and yellow classes split from the blue and green ones. And we can keep asking questions on our features, keep selecting features to split on that optimally split these classes up. So then we can answer or ask a question about height, do they have tusks? And, end up splitting all of our classes down until each node at the end only contains a single class. So at this point, we now have a built decision tree that then if we have an unknown sample, you pass it to this model, it asks these questions, and it tells you or predicts what the output is. Yeah, which I think is a pretty straightforward concept. Of course, though, these decision trees don't just have two levels like that. They tend to get very quickly large and complex. A tree depth of 40, which is pretty typical. If you make a binary split at every node at 40 levels deep, you end up with more than 2.2 trillion nodes. And it's no longer kind of tractable that you can map out all of those decisions that are being made. And of course, it's then, making much more complex decisions instead of just asking a few questions. And while decision trees are useful on their own, they tend to greatly overfit to your training set, which I think you can imagine. Building this single tree just from your training set, it might predict those values really well on your training set. But then if you pass it, information it hasn't seen before, it might not give you a good result or the right prediction. Instead, what we can do is train what's called a random forest. That's truly a forest of decision trees. And so each tree in your forest takes a random subset of training data as input. So each tree is built slightly differently from each other because you don't want these trees to be identical. And this is done through, this is called bootstrap aggregating or bagging, which is essentially, let's say you take a random 90% of your training set to train, a certain tree on, and then you put all that data back and you take another random 90% that's likely going to be different to train the next tree. So these trees are built in a slightly different way. Another important kind of feature of the random forest model is that a random subset of features are considered at every split in each tree. So instead of looking at your full feature set and picking the one that best splits the data at every split in each tree, it will only consider some of those at random. And this is really important because if it's picking the same feature to split your tree in the same spots every time, your trees are more or less going to be similar, even if they're using a slightly different 90% of the training data to build your tree. So you want these trees to be useful as individual decision trees, but slightly differently from each other. And really the goal is to then generalize better by correcting overfitting. So by fitting your trees in a slightly different way, what you can do is then pass your inputs to each of these trees and take the mode of the class that's given from all of these as the true class of the model. And another important piece here is that class bias can be corrected by adjusting class weights inversely proportional to class frequencies. So like I mentioned before, we don't have a lot of strong point load tests that were conducted to train the model on. What we can do is we can adjust these class weights so that it focuses on those strong cases more than the weak ones, because it has plenty of weak information to train the model on. And so now talking through the machine learning evaluation. So we can train this, huge random forest model, but then we have to prove, is this model accurate? And so to tune the model, we did cross-validation. So this was n-fold validation that was performed. Instead of doing a random split, taking a random split for the training data and validation data, we instead did this per hole. So you can imagine for each of these folds, each of the blue folds was a different drill hole. And so there were 19 of these total. So we made 19 different folds or different splits in performing the cross-validation. And so we felt that this was pretty natural that we would train the model on 18 of them, get results for that 19th held out hole, and then see how well the model performed. And so, as I mentioned in the other presentation, doing this cross-validation approach helps kind of greatly prevent overfitting the parameters of your model to the random forest and to a specific drill hole. And so how we visualized the data was by calculating a rolling mean on the predicted and actual class labels. And this will make sense when I show them on the next slide. But essentially, we predict point values that are the IS50 class that we convert to a mean value. But then what we've done is we've taken a rolling average of these values, right? The model can only predict 5 different values, but we want more granularity than that. And really, what we're interested in as an end goal isn't an IS50 prediction at one specific point. We want to get rock mass strength information from this. So it makes more sense to look at the predictions at a larger scale. And so we've defined a custom score here to validate the model as the percentage of these rolling mean curves that were within 1 MPa of each other. And so the actual class accuracy of the model wasn't amazing. And again, that's kind of attributed to there being a lot of noise in a point load test. And so, you know, it was a lot better than randomly guessing, but the class accuracy wasn't amazing. And so in kind of looking at these as rolling mean curves and using this score instead, you know, gives you a better way to look at how good the model is. And so visualizing some of these, this was the validation performance of the model. So these were holes that the model was not trained on, but then we made predictions. And so these were class predictions that we, you know, convert to IS50 values, and then using a 30-meter window, take a rolling average. And so you can see, you know, the model isn't perfect, but often it's capturing the trend in the actual data. And here's a few more. And I think kind of the real value here is, even though the model isn't perfect in this case, it can provide, you know, 600,000 point load test predictions in a few seconds. And so that gives, you know, the people at the mine much more strength information to work off of in creating a much more robust geospatial rock strength model. Because really, at the end of the day, they're interested in knowing what areas of the mine are weaker and what areas are stronger. And here are also a few examples of us doing this, using this same approach at a different mine. And so this mine actually had, you know, even more point load test information to train the model on. And we found that the model performed even better, you know, with more training data, which makes sense. So it could be that, you know, at Cadia East, the model wasn't perfect, having only 7,700 points, but, you know, we couldn't perform any more point load tests. And so at this other mine, we had 13,000 point load tests. And so we were able to get much better results here. You can see these actual and predicted curves are a lot closer to each other. And so we've since used this approach now at multiple mines with much improved results. And it's gotten good success. And so as this kind of goes to show that as you add more training data, the model's predictive capability improves. And then, of course, we can also look at feature importance that I mentioned in my other presentation. So once the model was properly tuned and we knew that it was giving a good result, we could tease out what the most important features in the model were using this permutation feature importance technique. And so shown here at the table at the right are the top 10 features resulting from the model of all of the features that were present. And so the features that we found that were the most important at the top here were many of the geotech and alteration related features. So this fracture frequency index that used RQD and fracture frequency, we see fracture frequency, RQD, the rock density, fracture spacing, alteration strength index related to the alteration minerals that were present, mineralization strength index, just what minerals were present in general, and so forth. And we found, surprisingly, kind of as a conclusion from this work, that rock type was not among the top 10 features. Instead, many of these geotech and other engineered features are near the top. And this was work that I actually presented last year at ARMA as well. And, you know, people ask questions about that, you know, isn't this wrong? But you have to remember that the model is picking what are the most important features for strength. It will tell you what the most important predictors are. And if you can prove that the model is not overfitting, this model is accurate. For this particular mine, at this particular site, these features were stronger indicators of strength than lithology. And it turns out that at Cadia East, the geological domain is heavily veined and heavily altered. So this actually made a lot of sense. And so now that we have this model that's, you know, properly tuned, we know it's accurate, we can go and then make predictions. And so we were able to make predictions at every meter along about 590 kilometers of core in just a few seconds. And so, however, even though we have, you know, 590,000 predictions, how do we ensure that all of those are going to be accurate given the input data? And so we came up with this confidence metric. This was defined as the percentage of features that were present weighted by the feature importance, right? Because you can imagine that, let's say you have various inputs, you have a core log that the model wasn't trained on, but you want a prediction of point load strength. You would pass those to the model. In some cases, though, they didn't have all of the core logs that were needed to make a prediction. Let's say they had the mineralogy information, but the geotech, lithology, alteration information was missing entirely. You probably don't want to make a prediction because you're going to be putting in possibly default or mean values that might give then a misleading prediction there. And so we only ended up delivering predictions that had a confidence greater than 75%, which was still 200 kilometers of core, which we thought was pretty good. And so greater than 75% would mean that more than 75% of the input data was present to make a prediction, but weighted by the feature importance. So making sure that important features are present. And so ending with some conclusions. So of course, data preprocessing is crucial. How you choose to represent and encode your data, is really important when you train your model. The model is the data. Handling bias and noise was really critical. We found that trying to do this as a regression problem instead of classification didn't work out well because of just inherent noise in the point load test and in the core logs. And then, of course, balancing between overfitting and underfitting, which you do when you go and tune your model. It's really important to apply domain knowledge to your model. So we found that many of these engineered features were important to the model. Had we not introduced those, the model probably would have been, of worse quality and wouldn't have given predictions that were as good. And so engineering new features from the logging data was essential to create an accurate predictive model of IS-50. And then kind of a final note, traditional intact and defected strength domaining may use lithology and alteration facies to set strength domains. This work demonstrated that many factors contribute to rock strength. And at Cadia East specifically, we found that these geotechnical factors were stronger indicators of strength than lithology because of the kind of heavily veined nature of the rock mass. And with that, I would be happy to take any questions.